Aloha class, here we go, part 3 of section 9.1, right? It is a monster of a section, so let's just keep going, all right? We've got to really plug through and get through a whole bunch of examples right now, so let's keep rolling. The direct comparison test. All right, let's say we have two sequences here, represented A sub n, B sub n. They both have to be greater than or equal to 0. Well, the series will converge as long as this is true and it converges, then we can say that A sub n also converges. Remember, we did a little bit of this stuff earlier this year, right? If B to the n, that series converges, and if A sub n is less than that and B sub n converges, well, then that means we can conclude that A sub n converges as well. Okay, let's say we have another series here, but let's say this series diverges and we have that information. Well, if B sub n is bigger than A sub n and A sub n diverges, then we know that this series must diverge as well. Now, one very important thing to note is that you always have to state your inequality whenever using the direct comparison test. All right, so let's go ahead and look at what some examples look like. I have my blank sheet also. So let me get out my notes. We're going to go to that blank sheet because it gives us a little bit more room to work with, okay? So we have these series. Whoa, snappity-dappity. Okay, we have the series of n equals 1 to infinity of n cubed over n cubed plus 1. Remember, first step when doing any of these guys is our nth term test. And as I do the nth term test, I get an answer of 1. Remember, as long as that is not equal to 0, then we can say that this particular series diverges, right, diverges by the nth term test. Okay, so that guy's done. Nice and easy, job on easy. Let's go to the next one. The next one, here we go. Ooh, pen. We have the sum. N equals 1 to infinity of 1 over n to the third plus 1. Okay, let's do the nth term test. My nth term test says, ooh, snap. That means it is equal to 0. Now remember, because it's equal to 0 does not mean it doesn't diverge and it has to converge. It does not mean it. It just means it's inconclusive and we got to try something else. So booyah! Right? Kind of looks like a p-series, but I can't use a p-series because I have something extra in the denominator. So I need something to compare that bad boy. And you guys are right. That actually, I'm going to use 1 over n to the third. Now, why am I going to use 1 over n to the third? Well, because I know 1 over n to the third converges by the p-series test. Okay, and then if I can just show that inequality that we had a little bit earlier in the notes, then maybe I can make some generalizations as well. So believe it or not, I'm going to start with just answering this question, all right? So I don't have to do a whole bunch of other work. Since, okay, the series from n equals 1 to infinity of 1 over n to the third, that's what I am comparing it to, converges, right? That would converge by the p-series test, by the p-series test. Okay, and if I had to say why, I would say because 3, right? My exponent there is greater than 1. And we know if that's the case in our p-series test, then we know it converges. Okay, and since I'm comparing this to something and I'm going to use a direct comparison test, I need an inequality. And the only way that this particular situation would help me out is if, right, I got to fill in these two blanks here, is if this came at the end. Because if that converges and this guy in the middle, which would be our 1 over n cubed plus 1, if this is true, then I'm golden, I'm donezo, DCT, right? I use the direct comparison test. Now let's check if it works out. Now, believe it or not, if your denominator, that denominator is always bigger. Well, if that denominator is always bigger than this guy, then that means this number here will always be smaller. So checkmate, that works out. All right, so since that p-series converges and we have our inequality that works out, we know that, so there's a lot of writing in here, right? We know that this original problem, which was the one that I was trying to answer from the beginning, right? We would say converges as well, and you guys write this out, as well, by the DCT. And remember, just get in the habit of writing that out. Write that out. Okay, by the direct comparison test. Boom, that's it. That's it. All I need is something that I know, an inequality that works out all the time, and then I can compare it. How about it? Not bad. Not too bad. Let's go ahead and look at the next one. The next one is, and when you're writing this guy down, or when I am writing this guy down, try to think very quickly what you would compare this to. Now, I don't know about you. I should always start by doing the nth term test. My nth term test for this bad boy, boom, equals 0. And since it equals 0, it doesn't mean it diverges. It doesn't mean it converges. It means it's inconclusive, and I better try something else. Okay, now this guy right here for sure looks like 1 over 3 to the n. And guess what? I can write, I'm going to just start answering my question since I'm going to compare this guy to the series that I know. 1 over 3 to the n, which would actually be 1/3 to the n, right? We buying that? And I don't know that 1 over 1/3 to the n, that converges. Well, how the heck do I know that converges? Well, it converges because it's a geometric series. And that geometric series has the common ratio of the absolute value of 1/3, which is 1/3. 1/3 is less than 1. Thus means it converges. So it converges by the GST, right? By the geometric series test. Now, if it converges, I need another piece of information if I am comparing two things, right? What's the information I need? Well, since I'm using this converges again, remember that means that guy has to go at the end, okay? And it means that always has to be bigger than this guy right here. And if I go back, oh, sweetie sweets, my marker ran out, but I got my trusty pen and I got more space, so we can do this. So the original problem here, which would be this guy right here, right? That is a plus sign. So that means that denominator is always bigger than that one, which means this guy would always be smaller. So check, check. It works out. Awesome. So then we can go, we know that. Apologize for the writing right now. We know that the original problem, which is from 1 to infinity of 1 over 3 to the n plus 2, converges, right? What do we say? As well. And then make sure you write it out by the DCT, right? The direct comparison test. Booyah! Let me get a new blank page. All right, class, let's keep moving, right? Let's keep moving. Let's go to the next one, which would be D right here, okay? And we have the sum, n equals 4 to infinity of 1 over the square root of n minus 1. And you might say, oh, well, let's first do the nth term test, right? That's going to be equal to 0, so that means I've got to try something else. Okay, I don't know about you, but that really looks like a p-series, right? That actually looks like 1 over the square root of n. And I know that the series from n equals, whoops, we're going from 4 this time to infinity of 1 over n to the 1/2. Well, that's a p-series where my p is 1/2. 1/2 is actually less than 1. And whenever 1/2 is less than 1 for a p-series test, we say that this guy diverges, right? So this diverges by the p-series test. We should always say, you know, how we know what's going on, p-series test. If they wanted me to do more information, I would say, you know, my p is 1/2, 1/2 less than 1. Okay, diverges. Oh, but we need something else. We need that and for this particular and, if it diverges, that guy, believe it or not, has to go in the middle. Because if that diverges and this stuff over here is always bigger than it, then I'm good to go, right? And it is, right? Because this is smaller. Well, if that's smaller than that, then that's always going to be bigger than that, right? This is bigger here, so that's in the right spot. If that's bigger, that's going to be smaller. So I'm good to go. That's a check. Then we can say we know that. We know that my original problem, n equals 4 to infinity of 1 over the square root of n minus 1, diverges as well by what? Class at home, by DCT, right? The direct comparison test. All right, let's just keep on rolling, right? This video, unfortunately, is going to get kind of long, class. I apologize for that, but too bad. So sad. All right, so we got n equals 1 to infinity. This time I got a little cosine dude up there. I got cosine of n over 2 to the n. Well, interesting thing about that is that's just going to fluctuate, right, class, between -1 and 1, right? That's the amplitude of cosine. So I could compare that. I could compare that bad boy to 1 over 2 to the n, right? And what do I know about 1 over 2 to the n? Well, 1 over 2 to the n is like 1/2 n. And we all know 1/2 n, woo, booyah, that's a geometric series. And that's a geometric series that has a common ratio of 1/2. 1/2 is less than 1, which means it would converge, right? So that converges by the GST, okay? And if I was able to talk about converging or diverging using something to compare it to, that means I just need an inequality. And since I'm using it that it compares by convergence, well, then that means that dude's got to be on the outside, right? Hopefully this comes true here. Oh, for sure. This is really like the same exact thing, except I have that guy up there that fluctuates in between a -1 and 1. So that means this guy right here will always be smaller than or equal. Remember, it can be equal to. So that means checkity check, good to go, right? We know that, right? We just go back to the original problem. We know that the original problem, n equals 1 to infinity of cosine of n over 2 to the n converges, right, class? As well by what? Say it with me. D, C, T. D, C, T. All right, what do we got? We got one more? Let's roll. Let's roll it, roll it, roll it, roll it, roll it. Right, the integral. N equals, where are we going from this one? Oh, okay, getting fancy. 2 to infinity of 1 over. You're probably like, oh, come on, Mr. T. That's easy peasy Japonesey. Right, I just got to compare that to the n equals 1 to, 2 to infinity of 1 over n to the 4th. Oh, snap, that's a p series. P's bigger, 4 is bigger than 1. So that means this dude converges, right? We know that this guy converges by the p series test, right? That's our rule. Okay, so if that's the case, then what do I need to work out? I need that and the inequality. This is a converged piece, so since it's a converged piece, that's got to go there, and that means this goes here. Man, that's got to check out, right? Let's see. That dude's small. Oh, what? That dude's smaller. Well, if that dude is smaller, then this is inaccurate. That is not true. Well, that means this dude is inconclusive using a comparison test. Well, snap, what am I going to do? Right, what am I going to do? I got to figure something else out. Well, guess what? We go back to our notes and booyah, or booyah, or booyah, or booyah. Oh, I can actually go to this guy right here, right? I thought I maybe had some notes, nudie notes. There we go. There are my notes. Okay, we did all those. I can't do it now. It means I need something else. What? Limit comparison test. Because if you looked at that problem, it looked like we were comparing, right? But it didn't work out in my favor. Well, if it doesn't work in my favor, I need something else to do. I'm not giving up. I need some more tools in the toolbox, right? So we have a limit comparison test. Well, what the heck does a limit comparison test say? Well, the limit comparison test says as long as your sequences are bigger than 0, if you take the limit of the original problem and what you're comparing it to, and it doesn't matter which one goes on top, doesn't matter which one goes on the bottom, right? Numerator, denominator, doesn't matter. As long as your answer comes up finite and positive, then you're good to go. You're good for the comparison, right? Whatever they both do the same thing. All right, so let's go back. Let's go back to that original screen here. And let's go back to this little stinker that didn't work out for us, right? Because I needed another tool in the toolbox. Well, first and foremost, I should have done the nth term test, right? And it equals 0, so I got to try something else. It might converge, it might diverge. I don't know for sure, so let's try something else. Well, I tried a direct comparison test because that looks like 1 over n to the 4th. And I know 1 over n to the 4th converges. But the inequality failed, so I got to try something else. Well, I still want to use 1 over n to the 4th because why? Because I know that dude converges by the p-series test. But now I got to try the limit. So let's just try this limit guy. Let's see if this guy works, right? It gave me some more tools. Well, that just says that I have to divide what I'm comparing, right? And that's what I'm comparing, divide it by the original problem. And once again, it doesn't matter what's in the numerator or in the denominator, okay? Let's go ahead and do this work. Let's see what we get. Oh, instead of dividing by a fraction, let's multiply by the reciprocal. Okay, and booyah, I got an answer of 1. Is 1 finite and positive? For sure it is. Well, then that means I can go ahead and make up a statement, right, class? So I could say, what would be a good little statement here? Since the series from n equals 2 to infinity of 1 over n to the 4th converges, okay, by the p-series test, and this time it's not an inequality, right, class? It is not an inequality. This time It's my limit, okay? So I got all my work. And the limit as n approaches infinity of 1 over n to the fourth over 1 over n to the fourth minus 10 is equal to 1, which is both finite and positive. And positive, we know that the original series that we were after at the beginning, n equals 2 to infinity of 1 over n to the fourth minus 10. Oh, what did it do? Converges, right? That's what we were comparing. Converges as well by what? Say it right now. Let's do it. LCT, right? The limit comparison test. So the one thing you're going to notice is a lot of the problems we just got done doing, you maybe could have used the limit comparison test also. If you notice this one here, we could not use the direct comparison test because the inequality did not work out. However, the limit did give me something that was finite and positive, so thus I can make a conclusion, okay? All right, let's keep on going with these problems. I think the next one, oh snap, do you know what I just noticed? I just wrote an entire problem down and it didn't get videoed. What is going on? Tell me it works right here. Not there either.